These are notes from Math 60, Melham's Math 60 class, Wednesday, April the 15th, section 8.3, page 711. I'm making a change to the assignment, skip problems 11 to 21. The original assignment went from 11 to 59 odd. Now we're going to skip 11 to 21, so only do 23 to 59 odd. We're dealing with equations that are quadratic in form. They're sort of like yesterday's assignment, but a little bit of a twist to it. Number 23, x to the fourth minus 17x squared plus 16 equals 0. We can change it into a quadratic like yesterday's if we let y equal to x squared. So if I rewrite x to the fourth as x squared squared minus 17 parentheses x squared plus 16 equals 0, then I realize by making a substitution, calling this x squared y, then it looks like a quadratic equation like yesterday. So if I let y be x squared, that becomes y squared. That becomes minus 17y plus 16 equals 0, and now it's quadratic. And in fact, this one's factorable. Whenever I can factor, I might as well factor, not use a quadratic formula if I don't have to. This is y minus 1, y minus 16 equals 0, which means either this expression is 0, y is 1, or this expression is 0, making y equal to 16. Now that I've got this problem solved in y, I go back and let y equal to x squared. So since originally this was x squared, so I now have x squared equals 1 or x squared equals 16. Then by doing the square root property, you basically take the square root and put a plus or minus. So it gives me x is plus or minus 1 or x equals plus or minus 4. If you want to double check, you can plug each of these back into the original. You'll see that they work. Problem 27, x minus 13 radical x plus 40 equals 0. This time I'm going to let y equal to square root of x. I notice that x I can think of as square root of x squared, quantity squared. So the original can be thought of as radical x squared minus 13 radical x plus 40 equals 0. And now I'll substitute let y equal to square root of x. And then I get the quadratic equation that I want, y squared minus 13y plus 40 equals 0. Factor, you have to think of two numbers with a sum of 13 and a product of 40, that's 5 and 8. The signs are both minuses, so y minus 5, y minus 8 equals 0. It gives me y equals 5 or y equals 8. But remember that the original was not in y, it was in radical x. So go back and change it, ignore the red for a moment. Radical x equals 5 or radical x equals 8. Now to get rid of the radical, you square both sides. So I have that in red, square and square, square and square. So x equals 25. Or x equals 64. Ideally, you go back and check these. You can check, I mean, there's nothing wrong with checking all the time, but they both do indeed check. I'll do a check later on for some problems, but not for this one. 31, a to the 2/3 minus 2a to the 1/3 equals 3. Again, it looks kind of funny, but if I let y equal a to the 1/3, this is a to the 2/3, which happens to be a to the 1/3 squared. So if I think of it as y being a to the 1/3, a to the 2/3 is a to the 1/3 squared minus 2 parentheses a to the 1/3 minus 3 equals 0. I will call each of these y. That makes the problem a lot easier. Coming back up here, it now looks like y squared minus 2y equals 3 equals 0. Factor, y minus 3, y plus 1 equals 0, giving me y equals 3 or y equals negative 1. And again, that's y, but the y is equal to a to the 1/3, so I'll substitute back a to the 1/3 equals 3, or a to the 1/3 equals negative 1. And what does raising something to the 1/3 mean? It means cube root. You might recall this is the power, 1 is the power, 3 is the root. So it's a to the 1, which is just a, and then cube root. So ignore the red for a moment. Cube root of a equals 3, or cube root of a equals negative 1. Then we just cube both sides. A is equal to 27, or a is equal to negative 1. They both happen to check if we would have plugged them back in. Now 35, it should be kind of obvious how to substitute. C plus 1 squared minus 4 times C plus 1 plus 3. Well, I notice that C plus 1 and C plus 1 match here, so in this case I'll call that thing y. That was actually the same kind of game we played over here, but here it should be more obvious. You say, oh, C plus 1, C plus 1, I'll just call this y C plus 1. And now I have y squared minus 4y plus 3 equals 0. This factors into y minus 1, y minus 3 equals 0, which means either y minus 1 equals 0, or y equals 1, or y minus 3 equals 0, which means y is equal to 3. That's y, but remember y is c plus 1, so replace y with c plus 1, so c plus 1 equals 1, or c plus 1 equals 3, and that gives me c is equal to 0 or 2. I will go ahead and check this particular one. Remember, it's a good idea to check all the time. I'll just do it occasionally here. So I'll plug in 0 here and here. 0 plus 1 squared minus 4 times 0 plus 1 plus 3. Is that equal to 0? That's a question mark there. That's 1 squared, which is 1, minus 4 times 1 is 4. 1 minus 4 plus 3 is indeed equal to 0, so that checks. And I'll substitute back in 2 here and here. 2 plus 1 squared minus 4 times 2 plus 1 plus 3. Is that equal to 0? Equals question mark. 2 plus 1 is 3, and 3 squared is 9. Minus 4 times 3 is 12, and 9 minus 12 plus 3 is also 0. So they both check. Problem 39, m to the negative 2 plus m to the negative 1 plus minus 6 equals 0. Now I could do this problem like the previous one and do a substitution, but in this particular case I'll just go to the definition of a negative exponent. M to the negative 2 means 1 over m squared. M to the minus 1 means 1 over m, so I'll just do it that way. And then I want to clear the fractions, so in red I'll multiply both sides by m squared to clear the fractions. So m squared times this, times this, times this, 0 times this is 0. So what I get in this step, if you ignore the red temporarily, it now has 1 plus m minus 6m squared equals 0. And now from here, there's a couple things wrong with it. First thing is I don't like that leading coefficient, that coefficient of the m squared. I don't like it to be negative, and it's also out of order. So to remedy that, I'll multiply both sides by negative 1 and put it back in order, which means the m squared comes first, and then the m, and then the 1. So multiplying negative 1 times 0, of course, is 0. Negative 1 times each of these will change the sign. So I'll change all the signs and put this first. So 6m squared minus m minus 1 equals 0. Then we factor 3m plus 1, 2m minus 1 equals 0. If you were to FOIL this back out, you get this. So again, by the zero factor property, either this expression, 3m plus 1 equals 0, or 2m minus 1 is equal to 0. Then I subtract 1, 3m equals negative 1, divide by 3, m equals negative a third. Or here, add 1, 2m equals 1, m equals 1 half. So my two solutions are negative 1/3 and positive 1 half. 43, ignore the red temporarily. 1 minus 5 over x equals 10 over x squared. Again, I'd like to get rid of the fraction, so now in red, multiply both sides by x squared. Gives me a nice equation, x squared minus 5x equals 10. Then I want to get a 0 on the right-hand side, so I subtract 10 on both sides. X squared minus 5x minus 10 equals 0. This one is not factorable, so we'll use our quadratic formula. So x is negative b. The opposite of b is the opposite of negative 5. That's 5. Plus or minus the square root of b squared. Negative 5 squared is 25. Minus 4 times a, which is 1, times c, which is negative 10, all over 2a, 2 times 1. This is a double negative, so I have negative 4 times 1 times negative 10. That's going to be 25 plus 40, which is 65. So 5 plus or minus radical 65 over 2 is my answer. I cannot break down 65 anymore. There's no perfect square besides 1 that I can take out of that, so we just leave that alone. Finally, 47. Wanted to show you this one because it's an example of a case where you actually have to check your answer involving radicals because one of the solutions doesn't actually check. So I'll let y equal radical x. Think of x as square root of x squared. So I subtracted 3 on both sides to make it look like this. So 2 radical x squared minus radical x minus 3 is 0. And I'll call each of these y. So I get 2y squared minus y minus 3 equals 0. Factor 2y minus 3, y plus 1 equals 0. Means either this expression is 0, 2y minus 3 equals 0, or y plus 1 equals 0. This one, add 3 to both sides, 2y equals 3, y equals 3 over 2, or y equals negative 1. Okay, again, that's y, but I have to remember that y was radical x. So ignore the red for a moment. So I'm going to have 3 over 2 equals radical x, or negative 1 equals radical x. Then I square both sides, giving me x equals 9/4 or x equals 1. This time, however, by checking, if I plug in 9 over 4 here and here, it actually works. 2 times 9 over 4 minus square root of 9 over 4, is that equal to 3? Then I have 9 over 2 minus 3 over 2 equals 6 over 2, which is 3, so that actually checks. But if I plug in 1, 1 is not going to work. Plug in 1 here and here. 2 times 1 minus the square root of 1, is that equal to 3? 2 minus 1 is certainly not equal to 3. So x equals 1 is not our solution. So the only real solution for this particular problem is x equals 9 over 4. All right, so these are notes for Melham's Math 60, Wednesday, April the 15th, section 8.3, page 711.